Good day! I'm Daniel Nico Moralpes from Mapua University. On behalf of our team, I will be discussing our thesis entitled Surface Roughness Analysis of 3D Printed Parts Using Response Surface Modeling. But before that, I would like to thank the people responsible for this opportunity to happen. First, I would like to discuss what a 3D printer is. 3D printing is also known by the name of additive manufacturing. This technology turns the design from a CAD into a real physical object. It also used by making a direct copy of an object with the use of a 3D scanner. Industries that use 3D printing technology includes aerospace, automotive, medical, and even in military. As an example, aerospace uses 3D printing to shorten or reduce the manufacturing runs, improve the performance, and become efficient by saving costs. For the automotive industry, it creates lighter and ergonomic tools used in assembly, and for military, 3D printed mounting sites for tanks are used to reduce the production costs. After the object has been printed by the 3D printers, some requires post-production works. These post-production works includes heat treating or sintering, polishing or sanding, cleaning excess powder. In this project, the researchers used ABS filaments. ABS filaments are mainly used for prototyping, especially in engineering due to its high strength and resistance to heat and impact. The surface roughness measurement test was done on the outside part of the specimen. In this study, the researchers used a contact-type device for surface roughness measuring, which was the SURF test SJ210. It can measure an arithmetic average of the roughness profile and the arithmetic mean width of the profile elements. For the statement of the problem, the research varied parameters on the 3D printer is needed to perform the roughness quality test, and after testing the specimen, the recommended parameters for 3D printing will be obtained. For the general objectives, the researchers is to identify surface roughness quality of 3D printed hollow rectangular parts made from the ABS material using a fused deposition modeling printer. For the specific objectives, to print 3D printed hollow rectangular objects with varying parameters such as temperature, printing speed, and layer thickness. To determine the lowest coefficient of the surface roughness considering the parameters, temperatures, printing speed, and layer thickness with the use of box-Benken design analysis. To identify the recommended temperature, printing speed, and layer thickness setting for fused deposition modeling using ABS material. For the significance of the study, we want to analyze and improve the quality of surface roughness of the design experiment using ABS material. Surface roughness can be improved by determining the perfect combination value of the three parameters: temperature, surface thickness, and speed. For the scope and limitation of the study, we analyzed the external part of the 30 by 30 mm hollow tube, which has the following parameters during the printing of the specimens. For temperature, 220 degrees Celsius, 230 degrees Celsius, and 240 degrees Celsius. For the printing speed, 40 mm per second, 50 mm per second, and 60 mm per second. And for the layer thickness, 0.2 mm, 0.3 mm, and 0.4 mm. The constant parameters are set to 90 degree raster angle, 0% infill, 100% flow, 1.5 mm filament, 0.6 mm nozzle, and 3 mm shell thickness. For the limitations of the study, the material used was ABS filament, and the study was focused only on the surface roughness of the specimens. The limitation of this study was that the insignificant parameters gathered during the analysis of data were omitted to ensure that only the significant parameters were discussed thoroughly. Now let us go to methodology. For the methodology, we, the researchers, started by planning and sharing ideas on how to perform this study. Next, we selected the parameters based on the related studies and journals that we read about 3D printing. Then, we researched on how to use the 3D printer, what filament to use, and the setting of the other 3D printing parameters. We designed the specimen using AutoCAD for us to start the fabrication or printing. We generated the combinations using response surface modeling in the Minitab 17. We have 15 base runs and we replicated it 3 times. So we have a total of 45 runs. For the measurement test of surface roughness, we used the contact type surface roughness measuring instruments, which is the SurfTest SJ210. For the data analysis, we used the main effect, interaction plot, and contour plot to come up with a conclusion. These were the constant setting in the 3D printer used during the printing process. This is the sample design generated. It's a hollow cube design with a 30 by 30 by 30 millimeter cube. Here were the varied parameters for the printing specimen. The design of the experimentation used was response surface methodology. The advantages for this design of experiment are it avoids the extreme combinations, it reduces the risk of failures, and reduces the number of runs. The device used was SurfTest SJ210 series 178 portable surface roughness tester in measuring the surface roughness of the specimens. After testing, the data is analyzed using the Minitab 17. The ANOVA results will be the basis in accepting the null hypothesis or the alternative hypothesis. We accept the null hypothesis when all the dependent parameters have no significant effect on the response. While for the alternative hypothesis, there should be at least one independent hypothesis to continue the study. After getting the p-value from the ANOVA results, it will determine whether to accept the null or alternative hypothesis. If the p-value is greater than 0.05, the null hypothesis is accepted. If the p-value is less than 0.05, the alternative hypothesis is accepted. Response surface methodology is a kind of effective method to optimize process conditions, and it can be determined the influence of various factors and their interactions on the indexes under investigation during technological operation. Box-Benken designs usually have fewer design points than central composite designs. Thus, they are less expensive to run with the same number of factors. Box-Benken designs always have 3 levels per factor, unlike central composite designs which can have up to 5. Also, unlike central composite designs, Box-Benken designs never include runs where all factors are at their extreme settings, such as all of the low settings. By looking into the ANOVA table, for arithmetic average height presented, we can see a highlighted row. It means that the specific parameters were significant to the surface roughness of the specimen. These parameters were considered significant to the specimen because the parameters were able to reach the confidence level of 95% or p-value of less than 0.05. For arithmetic average height, the parameters considered significant were the layer thickness, temperature, and the two-way interaction of printing speed and temperature. For the total height of roughness profile, the significant parameters determined were the layer thickness and the two-way interaction of layer thickness temperature. Main effect plots was the display of the means of each group to the parameters, printing speed, layer height, and temperature. The mean effect plot showed the difference in each level of the 3 parameters considered. The confidence level is set in the test was 95%. Any parameter reaching that value was considered significant factor to the sample data. For the arithmetic average height, the significant parameters were the layer thickness and the extruding temperature. For the total height of roughness profile, the significant parameter for the main effect plot was the layer thickness. Two-way interaction effect is the simultaneous effect of two independent variables on at least one independent variable in which the incorporated effect influenced the result significantly greater than the sum of the parts. For instance, the result of extrusion temperature interacted by print speed will have different outcomes as opposed by the extrusion temperature and print speed alone in obtaining the average mean surface roughness. The interaction between the layer height and the print speed for RA was just small. The researchers observed that the thinner the layers, the longer it took to complete the print. This is mainly due to the additional layers to be printed, and the rate at which the filament can be extruded to the tip was lower. As a rule of thumb, the print time tends to double as the tip moves one tip size to another. As we can see in the figure, the lines are moving closer to each other, but it doesn't intersect. This means that the interaction between the two parameters, layer height and extrusion temperature, is only minimal. As seen in this figure, the relationship between the print speed and mean of RA changes based on the extrusion temperature. For the extrusion temperature of 220 degrees Celsius, the mean of RA increases up to the print speed of 50 mm per second, then started to deviate. For the extrusion temperature of 240 degrees Celsius, the mean of RA decreases up to the print speed of 60 mm per second. Since the line in these figures intersects, this clearly shows that the interaction in layer height and extrusion temperature is significant. There is no intersection in this figure, but the lines are not parallel either. This shows that there is a slight interaction between the print speed and extrusion temperature. It was observed that at an extrusion temperature of 220 degrees Celsius and print speed of 60 mm per second, the mean of RT was at maximum. As we can see in this figure, the lines are moving closer to each other, but they didn't intersect. This shows that there is a minimal interaction between the two parameters, layer thickness and print speed. The contour plot showed the area where the value has the lowest and highest output using the colors on the plot. For this study, the lowest value for RA and RT were needed. Having a different combination, such as temperature paired with print speed, will have different results compared to the print speed with layer height. The contour plot below shows the different parameters being combined. This is the contour plot of RA for layer height and temperature. This is the contour plot for RA for the layer height and print speed. Contour plot for RA for print speed and temperature. And this is the contour plot for RT for layer height and temperature. While this is the contour plot for RT for the layer height and the print speed. And lastly, this is the contour plot for RA for print speed and temperature. Conclusion. Based on the ANOVA, the lowest mean of surface roughness happened when the layer thickness was at 0.2 mm. Printing speed was at 60 mm per second, and the extrusion temperature was at 240 degrees Celsius. RA is the arithmetic mean height across the microscopic peaks and valleys. It is good in assessing random surfaces because it is statistically stable. Since it was the go-to parameter when none is specified, it is available on even the least significant surface finishing measuring equipment. Basically, the total height of the profile measured from the highest peaks to the lowest valleys. The importance of RT is that it reacts sensitively to outliers and is used particularly to detect cracks in the boundary layer. The indicated surface finish parameters do not include information about the shapes, sizes of the occurrence and slopes. Having a higher optimal extrusion temperature of 240 degrees Celsius provided a better extrusion of the filament, which gave the filament enough time to liquefy. Under extrusion would be a problem if the extrusion temperature was not hot enough to liquefy the filament. This would cause the filament not to stick properly on the previously layer, resulting into higher surface roughness. Having a higher printing speed can speed up the time to complete the model, but having a printing speed higher than the recommended value resulted to higher surface roughness. The researchers found that having a higher extrusion temperature means that the filament can be printed using a higher printing speed of 60 mm per second, but if the extrusion temperature was set to lower temperature, it would result to a less intricate detail on the surface of the specimen. Layer thickness of the specimen was optimum at 0.2 mm. This supports that having a lower optimum layer thickness provided a reduced number of voids which were deposited during the extrusion of the filament. Printing on higher layer thickness gave a higher surface roughness value because the layers don't stick properly because of the voids present during the extrusion, which results to poor surface finish. The ANOVA showed that the significant parameters in the arithmetic average height were that layer thickness, temperature, and the two-way interaction of printing speed and temperature. For the total height of roughness profile, the significant parameters determined were the layer thickness and the two-way interaction of layer thickness temperature. That's all for the presentation. I would like to thank you for listening, and if you have any question regarding the presentation, you can always contact me. Thank you.